catalyst. Let's have a look at V2O5. That's the one there. It helps to create more of a bigger yield of SO3. Well, how do we get this SO3? It's created from iron and petroleum refineries or even steel mills, and they're harmful to the environment because nitrogen, carbon, and sulfur oxides are harmful. So, for example, our sulfur trioxide here is the one in question. Now, if we were to look at that for A, our labeled potential energy diagram, we would put our SO3 down here at the very bottom where it's lower on the potential energy scale compared to the reactants here. So I'm going to just draw it this way. So our potential energy is on the side, reaction progress is on the bottom. This is always going to be less than that because we have our heat that is created as a product, so we know that this is an exothermic reaction, so it has to be lower than the reactant. Using collision theory, explain why the rates of the forward and reverse reactions increase when this catalyst is used. Well, our catalyst is going to be right over there, right? This is going to be our V2O5. It makes it easier for this activated complex here to be hit as opposed to being up here. So it's easier for the reactant particles to hit that sufficient amount of energy threshold, and of course the molecular orientation as well to cross that activated complex so that it can proceed into that direction. Next, how does the catalyst affect delta H forward, our enthalpy change forward, and reverse? Well, we know that our delta H forward here is always going to be based on the reactant, and our reverse is always going to be based on the product in relation to the activated complex. So as you can see, the difference between these two is regardless always going to be the same, regardless whether the activated complex here is going to be lower here or middle here or higher here or even higher there. It does not matter. It's always between our reactant and the product, so that margin of distance does not change, so it doesn't affect. Next, catalysts like V2O5 are useful because they can occur in environmental favorable conditions where high temperature isn't necessary, like inside our human body. K2O is another type of catalyst in this Haber Bosch process, very important reaction. It's used to help make explosives and fertilizers. It can yield ammonia, or NH3 over here. However, this decreases the chance of a reverse reaction as well, since higher temperature isn't necessarily needed. When you use a high temperature, there is a chance that it can reverse in the opposite direction. Our ammonia will revert back to its reactants. We don't want that. So if we use a catalyst, we don't need this long temperature needed, so we can just create our yield of NH3, cut it off, and then use that. Next, we have amylase and xylanase. They are also enzymes, so they are a form of a catalyst. Now, when we get fibers of a plant, compress it, sheet dry it, we have to add chlorine, bleach, in order to whiten it, to make the paper white. We also use xylanase, which reduces the amount of bleach, so there's less chemical contamination. And we use amylase in order to help strengthen the paper. Next, I want you to try this question on your own. Please pause the video, give it a try, and I'll be giving you the answers shortly. This is the answer.